Recording has started.
Okay, welcome everybody to our TFTC webinar today. It's my pleasure to introduce my good friend, Dr. Sergio Batista. He'll be presenting today his latest research about dynamic traffic assignment for multi-regional applications of aggregated traffic flow models. Sergio has obtained his PhD in 2018 at the NTP and University of Lyon, France, under supervision of Dr. Ludovic Leclerc. He's now a postdoc researcher at NYU Abu Dhabi, working with Professor Monica Menendez. And his main research areas lie in the aggregated modeling of urban mobility, traffic flow theory, and ITS and sustainable cities. So, Sergio, the floor is yours.
Okay, thank you very much, Rafeg. Good morning, good afternoon, or good night, depending on where you are in the world. Thank you for joining this presentation. And in the next few minutes, I'll be talking about the work I've been developing for dynamic traffic assignment on aggregated networks for MFT models. So this is just an outline of the presentation. I will start by introducing what MFT models are. Then I will introduce how from our city network, our definition of the city, in which we have a set of links, we are going to aggregate this city into what we will call a regional network, where we will have to define a path or paths, where we are going to define the routing options for users. We will talk about the characterization of these paths, the formulation of the user equilibrium. Then we will see just a small layout of how all the framework works, and we'll discuss just an extension of the user equilibrium to bounded rational users, with just showing an example of how this framework can be applied. So just a brief introduction to the MFD-based models. MFD stands for the Macroscopic Fundamental Diagram. We have to scale our city network, in which we have just it's represented by a graph in which we have a set of nodes and links, as you can see here on this figure. Then we need to define our regions. How do we do it? We can apply clustering techniques, but these regions, they have to be at the end well-defined, compact, fully connected, and we have to ensure that the traffic conditions inside the regions are approximately homogeneous. This means that all vehicles traveling inside the same region will travel at the same average speed. So you see that when we apply a clustering to our city, we'll have, so this is just when we put the clustering on top of the city to define our regions, and then we have what we call our regional network, which is an aggregated vision of our network, considering the clustering we have done. And you see that the connections between the nodes, so here these nodes will represent the regions, and the arrows will represent the allowed travel directions from one region to the other, depending on the topology of the city network. So in this case, just to show an example, I'll be allowed to go from 2 to 1, considering the nodes that will be at the border, the allowed travel directions from region to the other. But this is not the case. For example, if I want to travel from 4 to 2, I'm not allowed, but from 2 to 4, I'll be allowed. So we have then the final regional network, and we are going to model traffic. How do we model traffic? Traffic here is modeled as exchange flows between adjacent regions. And inside each region, the traffic states will be regulated by the macroscopic fundamental diagram. What is the macroscopic fundamental diagram? Well, we can say that what is true for a link is also true for a region. And this means in a link we'll have the fundamental diagram, and the fundamental diagram regulates the traffic conditions inside the link. But we can also say that if we have a set of links in the neighborhood of this, in the same neighborhood, in which we have similar observable traffic conditions, we can group these links together in a region, and say, okay, the traffic conditions will be regulated by our macroscopic fundamental diagram. And the macroscopic fundamental diagram is just a relationship between the mean circulating flow in this region, or in this set of links that we created together, and the mean density. And how do we model traffic inside this region? It's modeled using a state variable called the accumulation, which is just the number of circulating vehicles inside this region, and the evolution of accumulation with time will depend on the balance between the inflow, so the number of vehicles that are entering the region, and the outflow, the number of vehicles that will exit the region. And depending on the assumptions that we make on the outflow, we can distinguish between two models in the literature: the accumulation-based model, where the outflow is approximately equal to the production MFD divided by an average trip length, or the trip-based approach, in which each vehicle will have an individual trip length to travel inside the region. And if we work out this formulation, we can just have this expression in equation 4 for the outflow, and if we substitute this in the differential equation of the previous slide, then we have a delayed differential equation to solve. So this is just to give you an overview of what MFD models are and how they work briefly. So now we will be talking about, for an MFD model, we have a network, but we need to assign people to travel on these paths in this network. So the first thing is, how do we define paths on this kind of network? So here we see different trips in the network with origins and destinations, and these trips will be defined by an ordered sequence of travel links, and these links will have a fixed physical length. When we put the clustering, so if we have the trips, we put the clustering on top of the trips, which is, then we have this definition of the clustering, we put on top of trips, and we'll see that the different trips will travel a different sequence of regions. As an example, these green trips here will be linked to this path when we do the aggregation, and the same thing, so we have a different trip, the blue trip, which will be linked to a different path on the regional network. And the same thing for this purple trip, and this purple trip represents what we define as an internal path. So an internal path to a region is just represented by a sequence of, it can be one trip or multiple trips that have an origin and a destination inside the same region, and that just travel inside this region. And here you can see just how these paths will look like on our I will call it maybe aggregated graph or regional network. So how can we calculate these trips? Well, two options. Either we have information about how to calculate the paths, either we have information about trips in the city network, which can be, for example, set of GPS traces if they are available. But in most of the cases, we don't have access to this information, so we need to build synthetic sets of trips. How do we do it? Well, we can just do, for example, Monte Carlo simulations. So we have our network. We are going to randomly sample origin and destination pairs in the city network, and we calculate just, for example, shortest paths in time. So this is just maybe a more naive way or a more naive approach to build the trips. We can think of other more sophisticated methods to do the sampling that can account, for example, for the demand. But for this work, let's just stick to this most simplistic approach to build a set of trips. Other way that we can think of is actually to calculate directly the paths on our definition of the regional network. And for this, so here we have just our city network and also the respective clustering that we did that allowed us to get our regional network. And we can also think on the more detailed vision of the regional network, in which we also consider the borders. So in this case, we'll have the nodes will be represented by the regions, and between 2 and 1 we will have the border 1, 2, which will be represented by this line here, and we can calculate directly the paths on one or the other, and for this we need to set up costs associated to the links, or in this case to the connections between 2 and 1, or between from going to 2 to the border 1, 2 to 1, and I set up different impedance functions for this based on exchange flows between the regions. So the maximum flow that's allowed to go from 2 to 1 as an example. The Euclidean distance between the barycenters, or the centers of gravity of the region. So in this case, it's just a geometrical center considering the Cartesian coordinates of all the nodes. We can also do, for example, shortest path calculations between the barycenter and the borders and the barycenters. And in this case, it will be a calculation directly on this graph. So we have a more simplified method also to calculate trips. So there are two approaches here. We have a way in which is building a synthetic set of trips. Other approach is calculating directly the paths on our aggregated vision of the network, for which we need to define cost functions. And these cost functions are just based on the criteria that I just told you, like the exchange flow between borders, Euclidean distance, or shortest paths between barycenters and the borders. So this was tested on the full Lyon network. We calculated for the whole network all shortest trips in distance, which gave us just a small number of 108 million trips, roughly, for all possible origin and destination pairs in the city. And when we aggregate this information according to the definition of topology, this gives us approximately 700 paths, including regional paths and internal paths. And we are going to investigate if the methods that I described to you in the previous slides are able to provide similar paths as the ones actually taken by drivers. So we consider a set of GPS trajectories composed by 673,000 real trips, which represent the month of March in Lyon. When we aggregate this information, it gives us 672 paths. And here we are going to check for two different definitions of the clustering for the city, as you can see here. And when you do this, we are going to check the similarity between the paths that we calculate between the first method, and the first method is when we have a set of trips, we just aggregate these trips according to the definition of the partitioning to define the paths. We do the same when we have the real GPS trajectories, and we are comparing the similarity levels between the method 1, which is the synthetic trips, the real data from the GPS trajectories, with method 2. Considering the different, let's say, settings for method 2, this means considering the different cost functions that I described to you in the previous slides. And we can see that for both, we have a good level of similarity. So this means between method 2 and the synthetic data and the real data. This means that this method, which is a much more simplistic and lighter way to calculate paths on regional networks, actually is able to identify on around 70% according to our comparison to the benchmark, which is the synthetic data and the real data, in terms of the similarity between set of paths. And we also see that when you do comparison between the synthetic, so when we build this synthetic set of trips, we are considering shortest paths in distance. But we know that people usually do not take or do not always choose shortest paths in distance. So is it fair? So how, when we do the aggregation, are we able to identify the same paths as the ones actually chosen by drivers? So when you compare both sets between the ones that I calculate using my synthetic data and my real data, we have a similarity value of around 80% for both partitionings of the network. So we have a way to calculate paths. The next thing is, how do we characterize these paths? So again, we have our trips, so our green trips and our blue trip. They will be associated to different paths because they are traveling on a different sequence of regions. And if we focus now on this gray region that is highlighted here, and we check the trips, each trip will have a different travel distance inside each region it travels. But they will be linked or associated to the same path on the regional network. So this means that the regional path that is defined by a sequence of traveled regions will be characterized by a distribution of trip lengths. So how do we calculate this distribution of trip lengths? The distribution of trip lengths is just calculated using our information of the trips, considering the information of the partitioning, and then we can actually aggregate this information considering different levels of what I call different levels of information. So the first level is, if I want to calculate a distribution of trip lengths for my green region, I aggregate all the trips that travel inside this region, no matter where they are coming from. So what is the previous traveled region and what is the next traveled region? Everything is aggregated to the most detailed level, in which we actually filter the trips by the associated path that they define, so by the sequence of regions they travel. And based on this information, we calculate explicitly the trip length distributions for each path, for each region that is defining each specific path. So just to show you one example on this small network, in which is the 6th district in city of Lyon, we see that when we consider the level 1 of information, so this means that I aggregate everything, I just have a single average value, no matter the path that is traveling on this region. So this means that I might have paths that in reality will just have maybe 100 meters traveling inside the region. I'll have other paths that might be 2 kilometers to be traveled inside the region. And since I'm aggregating everything together, I'm saying that they will have all the same travel distance, and this is what is represented by these blue crosses. And this is the most common assumption for application of MFD models. So we assume that and all vehicles have the same travel distance inside the same region. But what I'm saying here is, as we consider a more refined filtering of these trips, so focusing on the specific path, which is our level 4, we see that we will have different or a larger heterogeneity of average trip lengths, because we are calculating it by each path that travel on this region. And we can clearly see that our single value, our method 1, or the what I can call the benchmark, is not representative of the full heterogeneity of travel distance that I have inside the region. And this has a strong influence when we model traffic dynamics. So this is just to show you one example, and here we are just focusing again between method 1, which is I aggregate all the trips to define a single average travel distance for each region, to the most detailed level, in which I'm calculating for each region a different travel distance for each path that will cross this region. And we can clearly see that it has a strong influence on the traffic states, because a longer travel distance for a given path, since every vehicle will travel at the same speed inside the region, this means a longer travel time and a higher accumulation for a longer period. So this means that longer average travel distance might mean bottlenecks inside the regions, and this has a strong influence on how congestion is also propagated to adjacent regions and the whole traffic dynamics. So now we have a way to calculate explicitly the trip lengths, so the distribution of trip lengths. we have the traffic dynamics in the regions, and how are we going to calculate our network equilibrium, in this case, the user equilibrium. So what is important here is actually to notice that the travel time of a path connecting one given regional OD pair, which is just a sum of the travel times inside each region, is the ratio between an explicit distribution of travel distances and the mean speed. And this is the main difference when we talk about dynamic traffic assignment on city networks, because on city networks, our trip is just a sequence of links, and each link will have a fixed travel distance. In the case of regional networks, as we have seen, we have a distribution of travel distances that depends on the partitioning, so on how I aggregate my network. And this, of course, will depend on the topology that we have. So the topology of the city network with respect to the definition of the partitioning. And here, to calculate the dynamic user equilibrium and the stochastic user equilibrium, I just do a first-order Taylor series expansion of the travel times of a given path. So this is the sum for all regions, and X, it's my set of regions that define my regional network. And to calculate the travel times, I just do a Taylor series expansion around the mean value. And for the deterministic user equilibrium, we don't have nor the distribution of travel distances nor the mean speeds are considered to be distributed. So when you do this expansion, it's just the ratio between the averages. Or when we consider both terms to be distributed, so this means a set of trips and the mean speed, then we have this expression for the stochastic user equilibrium. Again, just to show you the differences, so this is when we calculate in traffic assignment the network equilibrium, we are using what we call quasi-static approximation or quasi-dynamic, depending on how we want to call it. This means that we have our simulation time, and we are going to split our simulation time into smaller periods, and in each smaller period, we are going to calculate our network equilibrium. And what happens for the next period, the traffic conditions will actually depend on the previous period. And this quasi-static approximation allows us to capture if, for example, the demand evolves. So if I have an increase of the demand, this will be captured, or to adjust to rapid changes in the traffic dynamics. This is why we are calculating the network equilibrium using this quasi-static approximation to capture the changes in this phenomena. And again, just to show you one small example on this network, which is the same network as before, we calculated this stochastic user equilibrium and the deterministic user equilibrium, and we can clearly see the differences between let's say, the influence of the explicit distributions of travel distances and on the perception of users to actually choose paths and how this can influence the travel dynamics. This is clearly seen, for example, in region 5 and region 6. So just the outline. If I can summarize everything in a framework, it will look like this. So as an input, we will need so we need to know the partitioning. The partitioning will allow to define our regional network or aggregated network. We need to have information about trips to calculate the paths and travel distances. Of course, the production MFD or the speed MFD. Based on this, we'll actually calculate the paths, we'll calculate the travel distances, and we have then here the loop of the method of received averages to calculate the network equilibrium. Just to discuss an extension of this framework to account for bounded rational users. What is bounded rationality? Bounded rationality comes from the seminal works of Albert Simon, in which people do not necessarily choose optimal options. So this means that in the case of traffic assignment, people do not always choose the shortest paths in distance or in time. Instead, they are choosing what is called a satisficing path. So what satisficing is coined for the junction between the words suffice and satisfy. So this means that the choice I will make will be sufficient for me and it will satisfy my criteria. My criteria is I want to choose a path that has a perceived travel time inferior to 10 or 15 minutes. And this is called the aspiration levels. The aspiration levels are just a set of constraints. And let's say how boundary rationality works. It's very simple. Just to give you one example, if I have 3 paths, one path has 10 minutes, the other 12 minutes, and the other 15 minutes. And I say, okay, I want to choose a path with a travel time inferior to 13 minutes, that I have 2 options that I can choose. The question now is, how are we going to choose these 2 options? So we need to define a search order, how we are going to assign the users according to their criteria. So we can consider preferences of users. We can say indifferent preferences. So this means that users are indifferent to choose any of these 2 paths if they satisfy their criteria, then they are perceived as satisficing, and they don't care if they'll choose one or the other because they will have a travel time inferior to the threshold. Or we can say users have, for example, preferences or strict preferences for the travel time reliability. Here, the travel time reliability will be basically associated with the variance of the distribution of travel times. And just to also tell you that in this case, we are calibrating our aspiration levels based on what we call the indifference band. And this is just the minimum of the travel time for a given OD pair. So we are going to test this on a different network, but it still has the 6th district of Lyon. So this is a network of the 6th, the 3rd, and the city of Villeurbanne in France. And we are going to simulate and determine emissions. So what is the influence of the user choices on the network-wide emissions? Here we are considering users that have indifferent preferences. So what happens if I increase my threshold for the indifference, or this means the indifference band? So if my indifference band is set to 0, this means that my model will give me the same result as the user equilibrium, but as I will increase my threshold, users will have this indifference behavior. This means that they will be equally assigned to both paths, because at some point, as delta OD goes to infinite, all paths will be perceived as satisficing. So this means that they will be able to choose, and you can clearly see that this has a strong increase in terms of emissions. And as you can see, these are just different settings of the indifference band, and we are calculating the relative differences between our boundary rational user equilibrium, considering the different delta OD values with respect to the deterministic user equilibrium and the stochastic user equilibrium. But then if we consider that users have a strict preference for their travel time, so we are focusing here on the value of reliability, so how they value the reliability of travel times, we can clearly see that this has a different trend in the emissions. So this is to show you one example of how this regional dynamic traffic assignment can be used for, together with MFD models to estimate the network-wide emissions. So just the takeaways from this presentation: we have discussed a methodology to identify and characterize paths. We also have shown that it's important to properly calibrate the travel distances of each path traveling inside each region, because this has a strong influence on how the traffic dynamics will be in each region, and this can actually be propagated to adjacent regions as well. We have discussed that when you do this traffic assignment, we need to account we need to account for the fact that the travel times are actually defined by a ratio between an explicit distribution of travel distances and the mean speed in the regions. We also discussed how we can extend this framework to account for the bounded rational users, the bounded rational drivers, for which we have considered the preferences of drivers when they have no preference and when they have strict preferences for the travel times. And just we have shown also an example of how this framework can be used to determine network-wide emissions. And this is just the list of papers for each of the parts, notably calculation of paths, characterizing the paths, characterizing travel times, and also the extensions to consider bounded rational drivers. And that's all that I have to share with you today. Thank you very much for your attention, and I'm happy to answer your questions.
Muito obrigado, Sergio. Thank you for your interesting presentation. So we are now open for the questions. I'll start by asking one question. So the regions that you divide the network to a number of regions. So do you do that in a static way or a dynamic way? Like, can you also have can it also change over time? Or
that is a very good question. So first, to briefly answer your question, because this we can have a long discussion about this, and I'll go to that point. Here we are considering static regions. So this means when you do partitioning, the partitioning is fixed. This is why the partitioning in this framework is given as an input. But if you want to consider dynamic regions, and let's say also an important thing is to ensure that when we do this partitioning in the static case, that we have regions that are compact. For example, that we don't have one region that sits inside of the other. That regions are fully connected. So this means that I should not have a blue link inside the yellow region. So this means that they are well defined to define my regional network paths, characterization of travel distance, etc. And you also need to ensure the homogeneity of traffic conditions. So these are the criteria that you should respect when to do a good partitioning from a traffic perspective. Of course, that we can consider other. So this is still for me a research question on how to properly do a partitioning, because if we consider maybe estimation of emissions, there's a given partitioning for that might be more feasible than if you want to do a control application. In terms of dynamic, and it's important also to note that when we do this, we need to also to calibrate the MFDs. So if we do dynamic partitioning, this means that at every time, I'll have also to calculate MFDs and to change everything. My question is, does it make sense to do it this way? I think that is open for discussion, and it's a difficult question for me to address scientifically. So I'm not sure if it makes sense to do a dynamic partitioning, but other people might have different opinions, and I think it's a question worth of debate, to be honest.
thank you.
I have a question.
Yeah, sure.
Yeah, so if the last presenter, the last question said obrigado, so of course I will say obrigado as well.
Thank you.
So I mean, I think it's related to the last question. Then I'm curious that whenever you said, like for example, 24 hours day, if the regions that was defined well, let's say for the morning peak, will hold also for the evening peak. I think you had some thoughts, but then just want to listen if you have some more further comments on that. If you have tested, if you try to, did some experiments related to that.
Thank you for your question. So this can be a long debate on how to properly define regions for these MFD applications. And just so far, if we just focus on the static, so if you don't consider any dynamics, it's still a research question, in my opinion, because the methods that we have discussed in the literature, at least the literature I know, they do not necessarily either they ensure topological features like compactness, like fully connectivity, but it's not sure that ensuring the topological features will also ensure the homogeneity of traffic conditions. So there is still this first question that we need to address to have a proper clustering for the network and MFT applications. When we include a dynamic, it's true that the patterns of traffic and congestion change throughout the day. In my case, I haven't done any test on this yet, but how can we approach this system? Maybe we can also consider something similar to our quasi-dynamic approximation when we do this traffic assignment. So this means that we will have here we have an outer loop represented by the blue box. We will need again another loop in time to change throughout the day also the definition of the partitioning, but this means changing also all the scenario and all the aggregation we did for we need to aggregate demand, we need to aggregate trips, so to define the paths and travel distances, we need to characterize MFD functions, and we also need to ensure when you do our partitioning, given the observable traffic states, what is the optimal number of regions in which I'm going to partition my network. So there are still for me a lot of questions here to be addressed. So far I have been focusing just on this, on everything that goes together inside this blue box, and right now I'm focusing on the partitioning, on the static partitioning of city networks to define our regional network and ensure the conditions that I previously stated.
Thanks, or obrigado.
Thanks.
Sergio, I have a couple comments.
Yeah, please go
Can
ahead.
you expand on the part where you talked about the quasi-equilibrium approach that you're using?
Yes.
I just want to understand how the time variable is treated in your model, because I don't see explicit time, right? So how do you go about time?
So I will just try to explain you first something. Here we have so we have our simulation time t. Let's say I want to simulate 10,000 seconds. I'm going to split my 10,000 seconds into smaller intervals, delta t, and my delta t can be 300 seconds, 500 seconds. So this can be adjusted to properly capture evolutions of the demand if it increases suddenly, if I have a peak of demand during my simulation period, or to adjust to the evolution of traffic conditions. So we have a time that goes, and at each delta t, let's say 500 seconds, I'm going to calculate my network equilibrium. In this loop, the method of averages convergence loop is actually, if I go here, it's represented here by my red box. And then when I go to the next period, so this means that I'm here, have I reached my end of the simulation? If no, then I go back and I can update my paths according to the previous period. And this is how I go from the initial period in which I have my warm-up and how I do my assignment throughout time. I hope I'm not sure if this answers your question.
And how do you ensure equilibrium then?
So the equilibrium, let's say if I go here, so what are the criteria I used? I'm following the criteria from Sveiti, his TRR paper 2007, in which I consider the gap, which is the difference between the travel times and the minimal travel time. And under perfect user equilibrium conditions, so in the deterministic user equilibrium, the gap will be 0. And if we are talking about stochastic user equilibrium, the gap will be a small value, very close to 0, but of course larger, because we have this perception of travel times that will have an impact on the gap. And for the bounded rational user equilibrium, I calculate the gap with respect to the definition of the threshold. This is on my GAT, Journal of Advanced Transportation paper that's on the list. So it's a more complex calculation of the gap. And I also consider the number of violations. So this means that I'm calculating the flows at each distant step, and I'm comparing the flow of the next step with the current step. If the difference between both are inferior to a predefined threshold, then I say that I have converged. If the number of violations is inferior to a predefined threshold, and of course we set up a maximum number of iterations.
All right, that makes sense.
So these are all the three criteria that I use combined.
Yeah. I have more questions, but let's see if the audience. So can you comment also on, maybe you mentioned it, but typically we make an assumption in congestion that the inflow cannot exceed the supply of the network. Are you doing that assumption? And
so this means in the traffic model, how do I?
Yes, are you constraining the input flow?
Yes, so basically I'm following the framework that Guilherme actually did, and it's published on his TR Part B 2019 paper. Actually, it's here the reference, and we actually have a constraint on the inflow, and then depending on how we also constrain the outflow, then we distinguish between the accumulation-based and period-based.
Yes, so can you explain that a little bit?
Oof, that is not my, so I'm using
okay. All right, I see.
Guilherme developed. And
usually what happens when you constrain the inflow is that you cannot get congestion in the network. I'm wondering if you saw that in your experiments.
I did so many experiments.
So it gets up to the critical density, but it never gets congested because you're constraining the inflow not to exceed, right? Which I find that it's a weak point of this theory. So I was wondering if you had any results.
I think, let me check if I remember correctly. I think that here, yes. I think that here we are going to the conjunction branch, and then you have a propagation of conjunction to the adjacent regions because of how we are constraining the supply.
So what's your critical accumulation?
Here it depends on the region. I don't know it by heart. I'll have to check the paper to know it by heart.
But can you pinpoint to a point that you know it's congested there?
Let me just check here the other one. For example, here this region, I'm sure that, for example, in the deterministic user equilibrium, it's conjectured, but in the DOE it's not conjectured, but in the stochastic it's conjectured. It should be around 3.5 meters per second, something like that. So in this region, you can clearly see a difference on both. So here we are seeing the difference of the perception in terms of the distribution of travel distances in the dynamics of the system, in which in one case the region won't be conjectured, but in the other case it will have an influence on conjunction. But
I guess you're not capping the demand then. You're not putting the constraint. If you had put the constraint, you wouldn't get congestion.
Yeah.
So I'm not sure. Yeah, I wish Ludovic was here.
To be honest, I don't remember by heart all the inputs that I have in my simulations. And we have played with these constraints as well.
Yeah.
But I'll have to check the paper for those details.
Excellent. All right. Any more comments? Very good, Sergio. Thanks so much for sharing your insight with us. And Rafa, do you know when our next webinar will be?
So we'll have our next webinar next week at the same time. We'll have another amazing presentation by Dr. Jack Haddad of Technion, Israel. And so I invite everybody to join that meeting next week. It will be last meeting of this year, and we'll have other interesting webinars next year, 2021.
All right. Thank you, Rafa. And thanks, everyone.